Guys, when I said when you hear the word specific, what does it mean? Divide by what?
Mass.
Exactly. So specific heats, we divide by mass, but also we divide by temperature. So what does it mean? Let me give you a good definition. It's energy required to raise a substance of, or maybe by 1 degree per unit mass. So per unit mass per unit temperature. So it's joule per unit mass per unit temperature. It's heat per unit mass per unit temperature. What does it mean? People are smart. They're looking for properties or characteristic of a system. So they come up with property which it does not change with the system. It's fixed property. For fluids or solid, liquid or gas, or even solid. It's called specific heat. Specific heat. What this property is? How people define it and what is it? So let's say I give you a container of water. This water has heat capacity of 4,200 joule per kilogram Kelvin. This is exactly the heat capacity of water, 4.2 kilojoule kilogram Kelvin. If this container has sand, let's say it has sand, heat capacity about, I don't know, 800. So they make some properties for even liquid, solid, gas, anything, even a gas, vapor. So what does this mean? It means if I want to increase 1 degree for 1 kilogram of water, I need this heat. If I want to increase the sand temperature by 1 degree, 1 kilogram, I need this heat. And this is a property. This is what? Characteristic of a sand, characteristic of water. Again, what is this? You have from high school, do you remember the very, very famous question in the summer? You see that that's the water in the summer, the water is cold and the sand is so hot when the sun is rising in the sky. But in the evening, like night, the water is warm, but the sand is so cold. Do you remember this question, guys, from high school? Does anyone remember this question?
I don't.
Yeah, this problem, very famous. If you go to the summer, the beach, you will see that the water is so cold, kind of cold compared to sand. Sand is so hot. You can't even stop in the sand. Like, it's very hot. But the water, kind of cold in the middle of the day, in the noon, yeah. But in the evening or even night, you see the water is warm, but the sand is cold. How come? Because of heat capacities. So water needs a lot of heat, longer time, because sun heat is the same. So it needs too much time, 5 times this, to get 1 degree up. So you can spend 5 hours to heat the water, just 1 hour here to heat the same temperature to the sand, because it has huge capacity. And opposite, if you want to cool down, this takes 5 times slower than this. This is so fast. So if you have a rod, or let's say of aluminium, it's 930 joule per kilogram heat capacity. So it's almost 1/4 or less of this. Put heat here, very fast will go there. Very fast. The heat conduct heat capacity, and it go away in very fast time. Like it cool down very fast. Unlike water, water has huge heat capacity. This is called specific heat capacity. Energy required to raise a substance by 1 degree per unit mass. Is it clear, guys? So the sun
Yeah.
heat is the same. Sun heat is the same. We need too much time, too much heat. Time is mean heat because sun give us Q dot. So we need too much heat or time to raise up 1 degree, 1 kilogram. But here, much lower time or much lower heat. So it very fast became hot, very fast became cold. In the night, it's very fast it became so cold for the sand. Very fast in the morning to be very hot. Correct? If you got some water and rod of aluminium, put them in the sun, you'll see the water takes too much time to be warm. Unlike the rod of aluminium or steel or copper, because of heat capacity of the water. However, when you cool it down, you see the water takes more time to cool down. It's hard to heat it up. It's hard also to cool it down. This is called heat capacity. We have two types of heat capacities. Usually you see 2 types, 3 types in this course. Everything 2 or 3. So we have 2 types of measuring heat capacity. We call it CV and CP. Even from their names, one is CP, heat capacity, and constant volume. This is constant volume. This is constant pressure. I measure it at constant pressure. For example, I got a container of water, constant volume, water. Then I heat it up. Heat it up, heat it up, heat it up. Then I measure CV of this water or gas, usually gas, let's say air. Then I heat up, heat up. I found out we need 717 joule per kilogram Kelvin. So for every kilogram of air to raise 1 degree, we need 717 joule per kilogram Kelvin. Let's say this is the same air, but in free piston movement. Like this is a free piston to move. Free to move, constant pressure. I put air also. This is called constant pressure process. I add heat. For this case, I need 1004.5 joule per kilogram Kelvin. 1000 joule per kilogram Kelvin. You see this number? I remember this number from maybe like your age. 717 joule per kilogram Kelvin. So I need for every kilogram of air to raise 1 degree at constant volume, 717 joule. In order to raise the same air, but at constant pressure, 1004.5 joule per kilogram Kelvin. I remember these numbers from when I was almost your age or even younger, high school maybe. This is called heat capacity at constant, specific heat capacity at constant volume, at constant pressure. So what the definition is here? The CV is du by dt at constant volume. CP is dH by dt as constant pressure. So here we deal with heat enthalpy, internal energy. Yes, U is joule per kilogram per Kelvin heat capacity. Enthalpy is joule per kilogram per Kelvin in heat capacity at constant pressure. So usually you always see CV with U, CP with H. CV with U, CP with H, enthalpy. Okay? Please open page 6.1 and read these comments. Page 6.1, open lecture 6, page 6.1. CP and CV are fluid properties. Regardless what the state is, what's going on, these are fluid properties. It's always this way. As long as you have pure substance, you have this properties. Fluid property, characteristic of the fluid. Behavior of the fluid. It needs how much energy to raise up 1 kilogram per Kelvin. It's independent of the type of the process. I don't care if I have constant volume. Yes, I measured CV at constant volume, but this is CV. If the problem is even not constant volume, this is my CV. This is my CP. So they measured, yes, by constant volume and constant pressure, but they are not related directly to the type of the process. Of course, because we are talking about raising 1 degree, it means delta T. So delta T Celsius, the same as delta T Kelvin. The change in temperature does not change. However, I recommend please to use Kelvin. Do not use Celsius. Use always Kelvin to make it be consistent. Because when you use equation of state, ideal gas law, when you use the other equations, it has temperature. It needs to be absolute temperature. Do not use any Celsius, please. Unless you are using the table, the steam table. You go with Celsius, in or out, input and output. But when you use equation, please stick to the Kelvin, absolute temperature. Okay, let's go now apply this for other cases. 4.4, this is section 4.3. We have heat capacity, the energy required to raise one substance 1 degree per unit mass. We have constant heat capacity with constant volume, heat capacity and constant pressure, Cp and Cp, Cv and Cp. Let's go now apply it for gases and solids. Let's start with gas. Gases are easier. Not easier, actually, it seems to be harder, a little bit more sophistication, but it's better for us. So 4.4. Heat for gases. Heat capacity for gases. Of course, we have two heat capacities, Cv and Cp. Heat capacity at constant volume, heat capacity at constant gases, as we discussed before, even ideal gases, if you want to discuss it. We have ideal gas, please, ideal gas, PV equal RT. Pressure, specific volume, gas constant, temperature. As gas constant, as you remember, it's universal gas constant over molecular weight, MW or M. Okay? And you have also H equal C U plus PV, correct? Enthalpy, specific enthalpy equal specific internal energy plus P specific internal specific volume, correct? Generally, these are two important equations. Keep them now. This is when you hear the word, even this is general, but this is ideal gas. Whenever you heard the word ideal gas, remember these two equations: PV equal RT, ideal gas law, and H equal U PV. Actually, H equal U PV, always correct. So these are the two equations, or the first one is a very important for gases. I'm keep saying gases because I'm sure one of you will use it for a liquid, maybe solid. Don't know how, but he will use it for something strange. So PV equal RT only for gases, vapor, superheated vapor, like air, oxygen, even vapor, steam of water. But when it's vapor phase, gas phase. H equal U PV, it's always correct. Definition of specific enthalpy. We have du, which is Cv dt. Correct? Because dV is du by dt. Or dH equals Cp delta T. Correct? We can integrate over process. Let's say 1 to 2. So the first one gives U2 minus U1 equal integration of Cv dt from 1 to 2. The second one gives H2 minus H1 equals Cv Cp delta T. You agree with me, guys? Why we integrate this? Because this is the exact differentiation. Integration is U. U2 minus U1. Here, this is exact. This is a property. It's not like delta W. It's not like delta Q. They are not properties. I cannot integrate them directly. I need to write them in terms of properties. but U isn't a property. H is a property. So now I can say delta U is CV, integration of CV delta T. So what happened? People able to measure CV as a function of temperature or CP as a function of temperature. So all I need, put CV here, integrate, get delta U. Put CV here, integrate, get delta H. Guys, now why I need delta U and delta H? Why? Do you know why? Why we need delta U and delta H? Can somebody tell me why? Why am I interested in delta U? Because this is first law of thermodynamics. Q minus W equal delta U. That's what we want. We want this. How much did we pay or how much did we get for this delta U? So there was a change in internal energy in a process. There is a change in internal energy. We always interested in the delta U. We always interested in delta H. Sometimes this and this is delta H. Sometimes Q equal delta H. Like when you have constant pressure piston cylinder. So we always interested in delta U or delta H. Okay? Okay? Thermodynamics engineer interested in delta U and delta H. How much heat did we pay to get Q or okay, okay guys, can you hear me?
Yeah.
Okay,
Yes.
now, so we have here several options. So delta U, integration is CV delta T. Yes. Delta H is integration is CP delta T. Yes, that's correct. Both of them is correct, are correct. Yes, that's correct always. Delta U equal this, but we can simplify. So if you go please to table, for example, table, I think A2. Go please open table A2. A2C. Open A2C. You will see that CV or CV bar per unit kilomole. So again, if you want R is molecular weight, R universal over molecular weight. CV equals CV bar times the molecular weight. CP equal CB bar. This is our formula. So here, this is per unit kilomole. This is per unit kilogram. Multiply by this molecular weight gives you this one is kilogram per kilomole. Correct? Divide? I think divide. Divide. Always divide. Divide. Yeah. Always divide. CV bar over molecular weight. CV bar. You can get CV or CP. Yes. Correct. So this guy, for example, is kilojoule per kilogram Kelvin. This guy is kilojoule per kilomole Kelvin. When I divide by molecular weight, it means kilogram per kilomole. Go back to this guy. So CV bar is another. When I have bar, it means I have. When I have bar, it means I have per kilomole. So table 2A, table A2A, AC, you'll find CV bar or CV function of temperature. For example, AT or A plus A0 plus A1T plus A2T square plus polynomial, like plus A3 T cube and so on. Something like this. This is a CV. If I want delta U, you're an engineer, you can integrate from T1 to T2. Put this here, multiply by delta T, integrate. So the first one will be multiplied by T. The second one, T squared over 2. The third one, T cube over 3. The fourth one, T power 4 over 4. And you have A0, A1, A2, A3, A4 for different gases. These are gases properties. You have them, substitute by them, integrate, then from T1 to T2, you can get the change in internal energy. Or we can, this is 2C. If you use table A to B, you can say C delta U, just simply CV average T2 minus T1. And CV average is CV at T2 plus CV at T1 divided by 2. So you can simplify. Take CV out of the bracket, integrate delta T, just change the temperature. So it's just CV average like this. And this CV average can be CV average or CV at room temperature, CV as you wish. So the lower the temperature is between T1 and T2, at lower pressure, the best this approximation is. This is the exact. This is exact. This is approximation. If you use even CV this, like CV room temperature, it's more approximation, the more simple approximation. We have example of this. Repeat everything for CP. So we have CP, function of temperature, like B0 plus B0T plus B2 T square plus B2 cube plus P4 T power 4. We want delta H. Delta H. It's integration of CP delta T. Put CP here, which is P0 plus P1T plus P2 T square plus P3 T cube plus P4 T power 4. Integrate with respect to temperature. It will be 0 T plus B1 T square over 2 plus P3 T cube over 3 plus P4 plus P3 T power 4 over 4 and so on. Substitute by upper limit minus lower limit. You get exactly delta H. So you can repeat everything for CP, delta H, and so on. Make sense? Does anyone have any question? A lot of questions here. The units joule per kilogram Kelvin. But if I put bar like this, it'd be joule per kilomole Kelvin. Kilomole. What is this? What is this, guys? Kilojoule per kilogram Kelvin. So kilojoule or joule per kilogram Kelvin. This is delta U over delta T. It means CV or Kelvin. Or kilojoule per kilomole Kelvin. Okay, so we're gonna stop here now. We have a quiz. Let's go take our quiz. Okay, guys? Actually, quiz we still have 4 minutes. Let's take something else until we go. I'm gonna clarify this. To the quiz is still with not still 11:40. Save and publish. But still we have still 3-4 minutes. Let's continue. So if you have any question, please let me know now. If you have any question, please let me know now. Does anyone have any concern? Any unclear? I know a lot of unclear, but any unclear thing now? So the problem, if you go please to lecture 6, problem 454. 454. Open please the problem 444. I said find delta U or find delta H for hydrogen. Delta U for hydrogen. So I'm gonna put it here in this side. Please, problem 454 in the book. It's page 363 in our lecture. I'm gonna go fast in this because it's related to this. And it's an important equation, important problem. UNG. 454. It is problem. He said, I want C delta U for hydrogen between temperatures 200, 800. T1 was 200 and T2 800. I think Kelvin. These are Kelvins. Of course, hydrogen is a gas. So we raise its temperature from 200. I want delta U. Of course, delta U would be in kilojoule, in kilogram, Kelvin, kilogram. That's it. The table A to C or A to B, it's a kilojoule per kilomole. You're gonna get kilojoule kilomole. After you're done, just divide by molecular weight. That's it. Divide by molecular weight. You're gonna get it correctly. So what? Step one is what? You have delta U. Let's say bar now because it's per kilomole. Integration of CV bar delta T. This equation in table A to C, please open A to C. You'll see this equation. When you integrate it, you will see something like this. A0 plus maybe T2 minus T1 plus A1 T2 square of minus T21 21 square divided by 2 plus A2 over 2 T2 cube minus T1 cube. Actually, this is 3 plus A4 T2 4 minus T1 4. Maybe 3 first, then 4. Yeah, correct. Something like this. Okay, guys? You have these A's are given for the hydrogen. You have temperature T2, any T2. You have any T1, plug in T1 and T2, you get delta U here, kilojoule per kilomole. Just divide by molecular weight. Table A1. You have all the molecular weights for all the fluids. Okay, guys? This is empirical formula A to C. If you set average, average is easy. Just CV at T2 plus CV at T1 divided by 2, which is table A to B. Table A to B. This table A to B. If you want room temperature, CV at room temperature, table A to A. Table A to A. Table A to A. And this solution is given for you in pages 63 and 64 in your. Let's take a quiz. The quiz started now, guys.